This recording is for Wednesday, October 21st, covering an example that I promised we will do today. Actually, we were going to do it on Monday and we didn't do it. So we're going to cover that example today. That's from chapter 27. And also, we will try to cover as much as possible from chapter 28 as we can. So again, it's going to be posted on Canvas and the discussion session. Do not forget that every basically time that we have a live class like this one, there will be a recording. I mean, there will be actually a discussion point that we will have, and that is graded for participation. So this is no different. Just a reminder that you guys are aware of that so that you don't miss this class or any class for that matter. Anyway, so let's get into the example that I promised last time we will do. So let me share the screen in here. So this is the example that last time I promised that we will do again, Eric, and we're going to have this one recorded. So basically, this is the example that I promised last time, and this is coming from chapter 27, problem 74. And I left the verbiage the way it's supposed. I mean, the way it's actually exists on in the book. So I did not change anything in it. The book has a drawing, actually, if I can remember vaguely how the drawing looks like. Let me try to draw that. So the whole thing is inside a magnetic field with whose intensity is 0.12 Tesla. So basically, let me use this pen. And the green is fine. So what I have in here, I have a wire that is anchored at the origin. Namely, this is a pivot point, and it has an angle in here that is making theta. Okay, it's equal according to the problem of 53 degrees. Okay, and it's held in place with a string, and the string must provide at least a tension in a T, and in addition to that, it has a definite mass, and the mass in here is equal to 0. That means it's subject to the force of gravity, basically, mg. And again, this whole thing is bathing inside a region where there is a magnetic field with a given value, and the magnetic field in this case, B in magnitude, is equal to 0.12 Tesla. Okay. The other thing that is also given in this problem is the fact that there is a current, and we have to have a current for this whole thing to run. So the rod carries a current I in the direction from towards P, and P I think is the pivot point. Yeah, that's where where the hinge is. So there is a current I going this way. That's roughly the drawing that we have in the book from this problem. And we're supposed to solve this problem trying to find, basically the question in here is to find the tension T needed for this to stay in equilibrium. In the bottom, it's stating to use problem from chapter 27, excuse me, 2770. So let's try to solve this problem using what we know so far. And it's static problem, by the way, because of the fact that this rod with a definite mass, so the mass is given also, the m is given to be equal to 0.084 kilograms. So given the units and the quantities that were given to me, I do not need to convert anything in anything. Everything is in SI. Okay. Granted that G, for my problem, I'm going to take it equal to 10 meter per second squared. Okay. I know that sometimes you're required to use 9.8 for accuracy, but if I'm doing rough numbers, actually, I don't mind putting 10 in this case. So those are the values that were given to me. Also, I need the length of the rod. The length of the rod, according to this problem, is 18 centimeters, which is 0.18 meters. I need to convert it if I need to use it at some point, okay? That's all the things that were given to me in this problem. And it's telling me at the end to use example from 2770 to calculate the torque due to the magnetic field force. As we learned from physics 4A, I know I did not have you for that class, but I suppose you did. The first thing we do in this case is draw the free body diagram for the rod, okay? So I'm going to have a new drawing in here. So this is the point P. So this is the rod for me. It has a length L, okay? It's making an angle theta with the horizontal direction, okay? And it's subject to a force that is acting in this point. This is the tension T. So the force is acting at a distance L from the pivot point. Okay, so we know the distance. It's actually making a direction, and I can actually find this direction using a theorem that we know back from the days of geometry. This is two parallels cut by the same line, so the inner angles must be the same. So if this were theta, this is also theta, okay? So that is easy enough to find that thing. So we have the tension. We have also the force of gravity in this case, and it acts by symmetry because we're assuming that this is a uniform rod in the middle. So this is mg, the force of gravity. I need to know the force, because in this case, this whole thing has a current I running through it. So there is a current I running in this direction, and it's bathing inside the magnetic field. I really have to use the right-hand rule to find the direction of the force, because if I assume that the positive direction is counterclockwise for torques, so this is the positive direction, it's clearly that the torque of this tension is positive, okay? The torque of the force of gravity in this case is negative because it's clockwise. So I need to know the direction at least of the torque of this this magnetostatic force, because I have a current running through a wire and it's inside the magnetic field. And remember, the expression that I'm going to use at the end for the magnetic field, and we already found that from last time, is the force is going to be the current times L times the magnetic field. L is the length of the entire wire, and it's sitting in a magnetic field. But I need to find its direction more than anything else, okay? But this is a force on an entire wire, but I need to find its torque, and that is a different. That's why it's referring to problem 2770 to find the torque, because the torque, I don't know where this actually acts. It acts in here. It acts in here. It acts along the entire wire, okay? So I need to find basically the torque of that force. But before I find the torque of that force, I need to know it's the direction of this torque. Is it going to be a positive torque? In other words, is it going to be counterclockwise or clockwise? Okay, so that's the question that I really need to answer quickly. So the current is running down toward P. The magnetic field is going toward the screen. So the force in this case must be pointing in the same direction, basically where the force of gravity is. So it must be perpendicular in every single point to this wire, okay? It may depend on the length or something, but that's basically where the force is, okay? It's clearly from this geometry that the torque due to the force of the magnetic field also is negative. So I have two negative torques, clockwise basically, and one positive torque, which is due to the tension. And this whole thing must be in equilibrium. Now, there are two conditions for equilibrium, if you guys remember from physics 4A, namely the sum of the forces equal to 0, and the sum of the torques also are equal to 0. It turns out for this problem, and most of the problems actually of statics, that it's much easier to work with the torque equation than to work with the force equations, because in this case, the force, the magnetic force is not clearly where it's acting, so it's going to be a problem for me if I'm trying to get its projections and things like that. So nonetheless, it's easier to do the sum of the torques. So this is what I'm going to do. I'm going to say the sum of the torques is equal to 0. This should be good enough for me to find the condition on this tension. So what I'm saying in here is the tension of, the torque of the tension minus the torque of gravity minus the torque due to the magnetic field must be equal to 0 for this one to be in equilibrium. This is from physics 4A. Okay, that's where we're getting this equation from. Now, I need to know this torque. So the torque of the tension should be easy enough to calculate, because although I don't know what the tension is, but I know where it's applied. And I know the distance from there, so I can calculate it based on the length L and based on this angle theta. The torque of mg also, I know where it acts, and I know its magnitude, actually, it's mg. So it's just mg times basically the arm length, which should be this distance, okay? And finally, the torque of the magnetic field is the one that I really need to refer back to problem 2770 to find it. So problem 2770 tells you the following. You have the same image, basically, same picture. You want to find the torque in this point, because finding torques depends on with the point where you want to find it, of the force, in this case, due to the magnetic force, which is, in this case, is going to be, okay, in general, if I take an element of the wire, not the whole wire, situated at a distance, let's call it R, okay, from the pivot point, okay? So the distance is R. Actually, the problem, I think they give you to use X, so I'm going to use X. Albeit usually I don't like to use X in this situation because of the fact that X refers to the X-axis. So distance X, so I'm going to take an element dx in here. An element dx by itself will be subject to a force that I can easily calculate in the, so the force, the magnetic force in this case is going to be I times the length of the wire, which is dx, times the magnetic field. It's the same formula that we derived last time. It's this formula, except the length of the wire in this case is just dx. So I'm taking an element dx of the wire. So this is how much force it is exerted on it, okay? The direction is perpendicular to the wire. Perpendicular to the current, to be more specific. So this angle must be 90 degrees. And if the magnetic field is pointing inward, so I know exactly where that force is. So again, in this case, okay? In this case, the current is raining down. Okay, the magnetic field is inward, so I know exactly where the direction of that force is. It's perpendicular. So its arm length is actually x. If you like, x times sine of 90 degrees, because this angle is 90 degrees. When you're calculating torques from physics 4A again, this is fresher from physics 4A, the torque of any force is equal to R crossed with the force itself, okay? And R in this case is X, and the force itself is F, which is given by that expression, and the angle between them is, I'm looking at magnitude. I don't care about the direction at this point because I know where the direction is. So it's a negative sign, but that's fine. Sine of 90 degrees, because this is the angle that we want to find. It's between R, the vector R, and it's actually negative sine, and the negative is taken care of by the direction of the force. So it's going to be a negative. It's fine. So it's this angle, okay? That's a negative sine degrees. But again, I'm taking just the absolute value because all I want is just the magnitude. And this is clearly 1, okay? So it's XF. So in this case, the torque of this force on that element by itself, situated at distance x, is going to be on the element dx only, is going, so that's a d tau. That's not the entire torque on the entire rod. It's just an element of the total torque. So all we did was find the torque on that element. So that's d tau. So it's going to be x times the force, and the force in this case is I dx times b. Now we have to integrate throughout the entire wire of length L. because we have to sum the torques. The torques is a quantity that you can add. So the torque is the sum from 0 to L of this quantity, which is xi dx b. I and b are constant. That's the current and the magnetic field inside the wire. And I'm left with integrating from 0 to L of the expression x dx. Clearly, the integral, if you guys remember from your calculus classes, again, what is the integral of x dx? Can you guys remind me? Just want to make sure that people are following. I'm not talking to myself. That's probably the simplest integral that you're going to have, okay, in this class, or any class for that matter. So glad that some of you are following. So the integral in this case is going to be IB divided by 2 for x squared evaluated between 0 and L, and that's clearly L squared over 2. So this is how this looks like then. It looks awfully similar to this expression. I mean, of course, I'm going to put the final answer first. But this looks like IB times L, which is the strength of the force as I wrote it up, times L over 2. I mean, this is not I mean, this is just numbers, so don't think of this one as some sort of a cross product or anything like that. It looks like the force times distance is L over 2, and L over 2 is just midway of the wire. It looks like this force is acting in the middle, and it's perpendicular. So that's exactly how this looks like, okay? But doesn't mean that it's acting there, but that's how it behaves in terms of the torque. It behaves as if the entire force is acting right in the middle, smack in the middle. So that its arm length will be just half of the wire, L over 2, okay? It'll be just in there. So that's how it behaves in terms of the torque. So we found this value. So I know this value now is equal to this much. I times B times L squared over 2. I need to find the other two torques though to complete the problem and then find the tension. So again, the tension of, let me draw it cleanly now so that we worry about it for right now. So the tension of the force of gravity, again, it's in the middle actually. So this distance is L over 2, okay? And I need to find, it's really L over 2 times mg times, again, I'm going to worry just about the absolute values because I already did the negative already. So if you don't know the sign, then you're going to take this angle as the angle for your problem. I know this angle is theta, and this angle is a complement of theta. So in other words, this is 90 degrees minus theta, and this whole thing then must be 90 degrees. So if this is also theta too, okay? So this whole thing then must be 90 degrees plus theta. So if I didn't know the sign, and similar to this problem, by the way, I would have run to the same situation in here too, okay? I would have put the sign of negative 90 degrees. So if you are really mathematically inclined and you don't care about the size at this point, you say, okay, I'm just adding this algebraically, okay? I don't care where the sign lands. So in this case, you say, okay, it's actually the angle because the formula for the torque from your physics 4A is R crossed with F. So R's come first. So I really need to look for R hat, R, the vector R, and F in this order and find the angle between them, okay? So in this situation, this is R, the vector R, and this is where the force is. So this is actually the extension of the vector R. So this is the direction of the angle that I need to find. So the formula would say then it's L over 2, that's the length. So it has no sign or anything like that, times the force, which is mg, times the sine of the angle between them, which is clearly from this geometry, it's pi over 2 plus theta, okay? There is a trig identity, and it's very important that you guys remember your trig identities, that says that the sine of A plus B is equal to sine of A cosine of B plus cosine of A sine of B. The only thing in here is A is equal to pi over 2 and B is theta. So this is clearly cosine of theta because sine of pi over 2 is 1. This is 0 because cosine of pi over 2 is 0. And sine of theta, then it doesn't matter because 0 times that number is equal to 0. So the whole thing boils down to cosine of theta, okay? Did I do something wrong in here? Yeah, but I measured this in the negative direction, clearly, okay? This is, again, the positive direction of the angles is always clockwise. I mean counterclockwise. And I measured this angle in a counterclockwise direction. As a matter of fact, I should have put 360 minus this stuff to really find it. So there is a negative sign in here. I hope you guys picked up on it. So the actual torque then will be a negative value from this perspective, okay? Cosine of theta. Because the whole thing is multiplied by -1. The sign is an odd function. So if you put the sign of negative something, is going to come out from the other side. Here is the deal, okay? There are two approaches to this kind of problems. And it's true only always when you're dealing with vectors. You can assign upfront your vectors. I mean, the sign for your projections, I should say, like I originally started doing, or leave them as they are, but they will emerge properly if you follow the math correctly. So in this case, if I left them positive, the sign would be negative. Or I could say that I know it's a negative torque because it's actually clockwise. Then in this situation, I just look for the absolute value, okay? So in this case, in that case, I will just ignore the sign. So in either case, it's going to have a negative sign in here. So we found the second torque, and it's minus L over 2 times mg times cosine theta, okay? So I found two torques so far. Let me change colors in here quickly. So we found this torque, and I know how much this torque is equal to. It's a positive torque. I mean, it's a negative torque too, I should say. And the negative torque is because it's actually, I ignored the sign and because I ignored it in here as a matter of fact, okay? Because it's the same reason, it's a negative 90 degrees. So it's a negative value of IBL squared over 2. So this is a minus IBL squared over 2. This is also a minus mg times L over 2 times the cosine theta, okay? The last torque that I need to find so that I can use this equation to find the tension is, as a matter of fact, the torque of the tension itself, okay? So here is where the tension is acting. Let me draw that picture again so that I can find that torque also. So we have the points. Here is P. The tension is acting in this direction from the geometry. This angle now is theta, okay? So if you like, this is what this distance is L, by the way. That's the length of the entire wire, a rod. And this whole angle, then you can argue that's 180 degrees minus theta, okay? And this is a positive angle this direction, okay? Because this is theta, this angle actually is 180 degrees minus theta. Again, I'm taking now the step, the rationale that I want the sign to emerge by itself. I don't want to argue whether it's clockwise or counterclockwise, assuming that the positive direction for the angle is always clockwise, meaning that this is a positive angle this way. And like when I was doing it in the for the other two, which was in the negative direction. Okay, so it's clearly then apply the same formula that we learned way back when we were doing physics for A, which is for the torque somewhere. Where is it? Here. This is the expression that we're going to apply. Okay. The length of L for R right now is L. So the torque for the tension now, it's L itself now, because it's applied the whole length of the rod, times the tension, which I don't know, and that's part of the thing that I need to know, sine, again, of 180 degrees minus theta. I don't have to put a negative because it's actually in the positive direction, from R towards the tension. Okay. Well, apply the same formula. Sine of 180 degrees, that is 0 actually. So this will be sine of 180 degrees, cosine of theta. Okay, the formula for this one also will give me a minus, because it's not a plus anymore, it's a minus, cosine of 180 degrees, sine of theta. Cosine of 180 degrees is -1 times -1, that's positive. Positive sine theta. So it already emerges as positive LT times sine of theta. Negative times negative becomes positive. So that takes care of everything right now. So I have the tension now, the last value that I was actually seeking for in this very same expression, that is the equilibrium of the entire thing. So this is now L times T times a sine of theta. Okay. Obviously L cancels because the whole thing must be equal to 0 for the equilibrium to happen. Cancel this L square, cancel that L square. This is one equation with one unknown. Theta is given 53 degrees. M is given 0.0 stuff. Okay, 84 I think kilograms. G, I took it to be 10. You can take it 9.8 if you like. Again, theta is given in this problem. I is given also 12 amps. B is given 0.12 Teslas, and L also is given because you'll be left with one L from the L squared of the magnetic force. Okay, and everything you're given. So technically, you should be able to solve this problem and then continue solving this problem. Does everybody understand the physics, though? Forget about the numbers for right now. Okay, so basically, yes, I'm glad to hear that's okay. So basically what you have a rod with a current running through it. Now, had the current been running in the opposite direction, the magnetic force is actually going to is going to help the tension in a sense. So in other words, in a different problem, but probably you could have, by the way, these kind of problems that we do in class, you're accountable for them in terms of preparation for the exam too. So this is part of the things that potentially could come in the exam. So you could put the whole thing in equilibrium with no need of tension. All you need is just put powerful current enough there, or powerful magnetic field enough there to put it in equilibrium, and it will not go anywhere. Okay, it's not going to go one way or the other. So that's one way of doing it. But the fact that the current was going toward the pivot point in this situation, it was actually trying to help it come down too. So it's working with the force of gravity to bring it down towards basically the equilibrium. But in this situation, of course, the thing is you need a tension to keep it from falling. Let's see if the expression makes sense, because again, that is in terms of the discussion, things like this you could discuss them in a problem like this one. So let's look at this expression again to see if it makes sense. I really want to put the tension now as a common factor in here. Obviously, mg will be to the other side positive, with the cosine theta over 2 and IBL over 2 also positive from the other side. So what happened to my screen now? It's not responding. Okay. So everything will move. So let me rewrite it quickly and see if it makes sense. Okay. So the tension then will become equal to mg cosine theta. I took the t as a common factor already. Plus, so it's a positive number. What is it? I times B times L, and the 2 divided by the sine theta. Okay. If theta were to be very, very large, 90 degrees, for example, sine of 90 degrees is 1. Okay. And the rod is actually smacked this way. It looks like this. So the force of gravity will have no torque in this case, because it passes by the pivot point. So in this case, cosine of theta will be 0. That makes sense. Okay, because then the force of gravity will not have any effect whatsoever on equilibrium. As a matter of fact, if there was no magnetic field, you don't need the tension at all. If B is 0, then, and the current is still running through this is actually a metastable condition. It can't stay by itself there. Okay, because nothing will make it go one way or the other. But the fact that you have a current running through it, and now all of a sudden you put a magnetic field, now that produces a force due to magnetism that is IBL in this case, okay, this force. That is going to try to spin it counterclockwise. You need to hold it in place in here with the tension. And the tension will be exactly to cancel this force, okay? Because sine of theta is equal to 0, but in this case, so that's in terms of the torques, it needs to be, you need to have to, because the force is acting in here actually, okay? So, and the tension is here. So that's basically how the, you need to put it in equilibrium, okay? So that makes sense in a sense that because it's trying to spin one way or the other, okay? Now, if theta is so small that it's practically 0, so this is how the rod will act. It still tries to spin it this way. Obviously, the tension in here will be along the rod itself, okay? And this will be an infinite value of tension in this case. It will be too much. As a matter of fact, there is no string that can hold it in place that way, okay? So again, as a matter of fact, all you need is just the force of gravity in this one. I think you had a problem like this one for the holding the sign, basically, for carrying signs for, how does the picture look like? For carrying a sign, for example, in posters, okay, and how much tension it is needed to hold it in place. That was from physics 4A. Again, now you have just the addition of physics of this magnetic force. Does this problem make sense to you guys in terms of how to solve it? So you have the equilibrium condition for torques. The torque for the gravity is easy to find. You have to pay attention to the signs, that's all. It's clearly negative torque because trying to spin it counterclockwise. I mean clockwise, I'm sorry. And the torque of the tension has to be positive in this case, counterclockwise, to keep it from basically falling. So that makes sense. Now, the torque in this case for the force of gravity, because for the magnetic force, because of the choice of the direction of the current is also clockwise. It's also trying to help the force of gravity bring it down. So the tension has to be higher. It has to counterbalance both things, both of them at the same time. Okay, both forces in the same time. Okay, so this is problem 74 from the book, from toward the end. Any other questions? Any questions at all? Good to go? Yes, what's the question? Oh, good to go? Yes? Okay. I'm sorry. You guys know the trick, I think. Yeah, usually the tricky thing is the signs, okay? I agree with you, Sebastian. The tricky thing is the sign. You really have to look at the problem from the intuition part of it, okay? Ignore everything. It's clearly gravity. Okay, I'm sorry. Let's put back, okay? The easy ones are easy. Like, for example, gravity is pulling down and the tension is on the opposite side. So whatever signs you choose, both of this have to be on opposite sides of the equation. It is, and I agree with you, Sebastian, on this issue, is the one for the magnetic field. You really have to have the right-hand rule properly used. The one first is for the direction of the current. The magnetic field is into the screen, into the page, okay? So the force is in this side, the same side where the gravity is. If you have that, then since it's in the same side of the gravity, then wherever the gravity is, that is also where the magnetic field is. It is a headache, usually, when we're dealing with this part, with the signs. So you really have to pay close attention to the signs. And if this is not bad enough, you will see more sign issues today. So it's only going to get a little bit more involved today. Okay? Sorry, but that's how things are. Okay, so let's move on. So chapter 28 is today's topic. We're going to talk about what is really magnetism, okay? If you Google my name, Jamoy Bouzidi, you'll see that they have one publication, that was a long time ago, with Professor Harry Soule. And it was really on magnetism itself, okay? That was one of the things. Professor Harry Soule was my thesis advisor at UCSD, was known to be the smartest, is still alive, by the way, the smartest person, not the most knowledgeable person about magnetism who's alive. That's basically how he was dubbed by some of the physicists. And it's still the history of magnetism, or when it was discovered, is one of the things that probably go way back. Okay, when we were lab, I used to tell a story. Of course, it's a nonsense story to basically illustrate the point that I personally don't know when magnetism was basically discovered. But that's another story for another day. Anyway, we will try to understand what is magnetism, what produces magnetism, and it's no secret that magnetism is produced by moving charges. Okay, so that is basically how experiments early on indicated. And we're going to dig into those experiments basically to have a quantity now to measure with it the magnetic field. And from there, we're going to start calculating the magnetic field. Okay, you will soon see that that expression is not only the easiest expression that you will see in your physics sequence. As a matter of fact, I could probably put it to the top of the most complicated formula that you will ever see in the physics 4D 4 sequence, from physics 4A all the way to 4D. Okay, so it's going to be ranked the top one. Once you go through that step, things start to become easier, and we're going to use that to solve problems with it. After that, we're going to discover Ampere's law. And Ampere's law should be easier in a sense to do the same things when you have symmetry, of course. It's going to be similar to Gauss's law when we did it way back when we started this class in chapter 22. Okay, so that's going to be very helpful. And then we're going to try to put everything together. We're going to try to apply, first of all, Ampere's law, and then we're going to put everything together. And that is when Mr. Maxwell, as I said last time, discovered that there is something the matter with actually Ampere's law itself. Okay, and he had to correct it. In doing so, he's put another term to it, and the equation now became symmetrical. And all of the equations that I'm going to write hopefully today or Monday, they solve everything we need to know about magnetism, about electricity, about light, about optics, about wave optics, that is, or even geometrical optics. So everything we know, we need to know. This work of Mr. Maxwell inspired other physicists, the least of which, of course, is one of the greatest physicists who have ever lived, Albert Einstein himself, to seek new physics, to explain new problems in physics, or at least modern day problems in physics. And it's still inspiring other people actually to work on a grand unifying field theory. So this is big. So I'm hoping that you guys will evolve with me and move with me through how big brains, basically, that humanity have ever known, basically thought the process through and came up with solutions to problems in physics, and that still inspired other basically ambitious physicists all around the world to basically walk the same steps that they did. So I'm hoping that one of you guys or all of you guys do the same thing. Okay. Anyway, and then we'll try to understand what magnetic materials are. Anyway, so as I said before, experiment, or let me start a new page. I want to keep this one clean in here. So observations have shown that if I have a charge moving with a velocity v, okay, and I'm going to say, for the sake of argument, assume that q is positive, okay. If it's negative, everything is going to be reversed, that's all, so don't worry about that. So if it's moving, it's going to create a magnetic field, and that magnetic field is given experimentally by the following expression: mu naught over 4 pi times q times the velocity divided by the distance squared. So this is experiment. So don't ask me to prove this expression based on observation, okay? This is basically how this expression is, you can devise it, okay? So again, a point charge, q, produces a magnetic field proportional. Remind me, Sebastian, because you have asked you've raised a very important issue, because that is actually the bulk of the problem, not this one. Not what I'm writing. Right now, it's a little bit easy enough. So it's proportional to Q, to the charge itself, and its velocity. So it's important that it has to be moving. So if it's not moving, it has no magnetic field. Okay, and inversely proportional and inversely to the square of the distance. First thing first, what in the world is that mu naught there? Okay, mu naught is a constant that is chosen to actually part of the definition of the ampere to be equal to, it's a constant in vacuum, to be 4 pi times 10 to the negative 7. Let's think about the units in here. It clearly has to have the units of a Tesla in here, because the magnetic field is measured in Tesla, and it has to also have a meter squared in it, because that is part of the definition of the distance, which is a meter squared, divided by a Coulomb to cancel this Coulomb from the Q, and divided by a meter and multiplied by a second. So basically, this is how this whole thing needs to be then. The units for it are going to be a Tesla to make it work from the other side, times the distance squared. I'm going to cancel one of these terms, times the divided by a Coulomb, divided by velocity, which is multiplying by s dividing by m. So one of these m's cancel. So the units in SI are Tesla meter second over Coulomb. Look at this Coulomb over second. That is actually an ampere. So it is actually a Tesla meter per ampere. Okay. So that is the unit for it in SI. Okay, Tesla is not actually a fundamental unit. So Tesla, again, we defined it last time. Remember from the expression, any expression now, the expression that we used last time, B times I times L, gives me the force. That is clearly in Newton on one side, meter times an ampere times a Tesla. So in this case, the Tesla itself is a Newton divided by an ampere and meter. So in this case, if you divide it that way, so mu naught itself will have, what is it? A Newton times divided by an ampere meter, and then times a meter divided by an ampere. Cancel the meter and the meter, and now all of a sudden you have a Newton divided by an ampere squared. Somebody complain and say, wait a minute, Newton is not actually a fundamental unit, and you're absolutely right. So it's actually a kilogram meter per second squared ampere squared. So that is the unit of mu naught, not its value, by the way. Okay. So it's in kilogram meter per second squared per ampere squared. Okay. So that is the unit, because again, in the SI system, meter, kilogram, and second and ampere are the fundamental units. So you can remember it whatever way you like. Most of the times I put SI in here, honestly, because of the fact that if everything is in SI, distance is in meters, time is in second, mass is in kilogram, what is it? Currents are in ampere, charges are in Coulomb, forces are in Newton, everything is in SI, basically. Pressure is in Pascal, everything is in SI. This guy will be in SI. This is its value, 4 pi times 10 to the negative 7. Now, if somebody is using different units, like the CGS, for example, centimeters, grams, and other things for, and Gauss for the magnetic field instead of Tesla, the number will be different, will be shuffled all over the place. So, okay. So, but at this point, this is an easy way to remember it. So we know the value of this value mu naught from, again, definition of the ampere, actually. And this is the expression for the magnetic field for a charge. Now, if I have a wire, and if I take an element of a wire, okay, that has a current running through it, I can argue that the charge Q times V in this case, which is the charge per unit time, can be the same, at least dimensionally, in terms of this is a point charge, by the way, as an element of length. In this case, I'm going to call it dl. So this element dl is sitting in space. Of course, you cannot have an element of a wire sitting anywhere with a current running through it I. That doesn't make sense. Okay, but take any element that is probably stretched all over the place. So this is how the wire potentially looks like. I just take an element of it of length dl. Then in this case, I can argue, and it's actually based on observation, so do not ask me to prove this expression too, that this will create, because I'm taking an element d now, dl, not the whole wire, that is going to be given by the following expression. And I did not answer your question yet, Sebastian, the one that you raised earlier in the problem, because it's the same question. It's a valid question about the directions. Everything is probably easier in this situation, except when you have directions. And here is your direction started in. So this element of wire dl creates an element of a small magnetic field dB, if you wish, given by this expression mu naught over 4 pi times IDL cross product with an r hat divided by r squared at a distance r from this vector. So let me take a point in space, call it this point. Actually, it's not good to draw it in here. Let me draw it in here. Okay, point in space P. This is what I meant by r, the distance between this element and this point, and this is what I meant by r hat. The magnetic field in this case is going to be given by this expression. This is again, that's actually the law of Biot and Savart. Those are two French physicists in the 1800s who formulated it based on observations. Again, this is experiment. Okay, so this is the law of Biot and Savart. Okay, so that's basically how Biot and Savart. Okay, so those are the R is kind of, you have to eat it at the end. Don't. I mean, you have to just have its head poke up. I mean, so that you can see a little bit of it, not the entire R. Okay, Savart. Okay, so this is their law. Okay, so this is the expression. Again, I'm not calculating the entire magnetic field, and I did not represent the magnetic field in purpose. Okay, because this is a cross product. Okay, so the dl is clearly in this direction, and the r hat is in that direction. So if I use this law, the r crossed the dl first crossed with r hat is going to give me a vector perpendicular to them. Okay, both of them. So if this were the dl, the vector actually is going to be perpendicular on both of them. Okay, and provided that they're making an angle between them of some sort. They don't necessarily have to be perpendicular. Okay, so this is the expression that we're going to be using to actually solve our problems in here. Again, mu naught is given by that, and it was inspired by this one. As a matter of fact, it's the other way around. So let's address this issue of that Sebastian has raised earlier, which is the direction, and that is basically how this expression raises it in here. So in this case, in here, the direction. Let me go back to the screen. B is perpendicular. Sorry. Perpendicular. Let me write it much easier. Perpendicular to V and the unit vector from where Q is to where we want to find B. Okay, Direction usually is a nasty part of the whole problem. Okay. So that is basically how this expression looks like. Okay. So I hope that I have addressed the issue more or less, Sebastian, and I know it did not completely, honestly, fulfilling give you a full description of it because it really has to go through this cross product. Now, the magnetic field at any point in here, you have to sum through the entire wire to find it. So the actual magnetic field in here, to be truthful to this expression, you really have to sum through the entire wire. Mu naught over 4 pi. This is in vacuum. If it's not in vacuum, you have to have different mu. The integral through the wire of IDL, and I has a potential of change actually, but for right now, we're going to assume it's constant. DL is a vector crossed with R hat and divided by R squared. This is a very, very nasty expression. This is as ugly as it can get. I don't know what that red thing is in there. Is it from before? I cannot delete it. Please ignore that red marker in there. Okay. Apparently it's from before. Okay, let me redraw this diagram so that you guys see it. Okay. So what I have in here, I have an element of wire, DL. Its direction is the direction of where the current is. Okay. And I said, okay, I am here. I want to find the magnetic field in this point. Doesn't matter. Let's put it in here. I don't want to have to deal with a negative thing. Situated at an R from this element. So that vector is R. This is the R hat. Okay. This is where the DL is. I'm sorry. That's fine. It's parallel to it. Okay. Then the expression of the magnetic field in that point due to just that element itself is mu naught over 4 pi times the current I times DL crossed with this R hat, the unit vector point where the radial direction is from the point where I'm calculating, divided by R squared. This R squared is not from the origin of the axis somewhere, okay? I'm not assuming that this is R. This R is actually, this is probably, you can call it R prime if you like, and this is the R that interests us, okay? So it's not, so this is probably where the wire itself has its own unique coordinates, probably R, okay? So this is complicated stuff. This is not easy, at least to deal with in terms of algebraically. So when we're dealing with problems, we have to really make them as simple as possible in order to calculate this thing. So compare this with Coulomb's law. That really we were able to find the electric field. The electric field due to a charge distribution of some sort was 1 over 4 pi epsilon naught times the charge, which is dq, okay, divided by the distance squared times r hat, okay? There was no cross product there, okay? So if dq happened to be constant, q was uniformly distributed, all you have to do is integrate it 1 over r squared, depending on the direction where we are, okay? And you find the contribution of the different points in here. So if you have a distribution of charge in here, given by dq, which is equal to some rho times dv, then you can find in here the electric field anywhere in that direction just by doing this summation where r hat is again this direction for that element dv, and you sum through this entire volume and you find the electric field in there. So that was a little bit easier. And here you have a wire that has some sort of a density in this case that you can use also similar if you like. So the integration is through the wire itself, okay? And you want to find the electric field, but everywhere that you're trying to, magnetic field, I'm sorry, everywhere that you are doing that, you have to cross this product and find a vector that is perpendicular to them, okay? And that's what makes it more difficult than this expression, okay? Because you have this cross product that you're dealing with. Other than that, it's to some extent similar. 1 over distance squared is similar, 4 pi is similar. And the other thing that we clearly immediately notice is whereas epsilon naught, the permittivity, was living downstairs, now the permeability, that is what this mu naught is called, is now living upstairs. So this is actually the permeability of vacuum. Permeability of vacuum. Okay, well, exclamation points. Okay, so that is a term, the term for this expression. Here again, to tells you how much magnetic field you can have in a region depends on the properties of the medium itself. Okay. Do you guys see this law? Yes. This is as complicated as you're going to ever have it in this series of classes. It's this expression that we actually have to start using now. Whoever wants to. Okay. So let's do it for a long wire. Let's actually do the calculation for a long wire. So that's part C in here. So let's do the actual calculation for a long wire. How are we doing on time? We still have time. Good. So imagine with me that I have a wire. I mean, the book had it a little bit different, so I'm going to have it the way that I normally have it. So I have a wire of length 2L. So I'm going to go negative L and positive L, and I'm going to go in the middle, and somewhere in there at a distance y from the wire, I'm interested in trying to find where the magnetic field is. I'm going to assume that there is a current I running from the negative side to the positive side. So there is a current running this way. So if there is a current running that way, I want to find the magnetic field produced by this wire. So magnetic field produced by a straight wire to make the calculation easier, because then the integration is, instead of being in space, it's going to be simply in 1D. Okay, straight wire. I always hit this button and then the E comes out. Okay, straight wire, and of length 2L. Okay, and we want to find B, the magnetic field, at a distance y from the center of the wire. So that's the question really that we want to find. Okay, that is what we're interested in. We're trying to find that expression. So we want to find B there. Okay, so again, similarly to before, I'm going to take an element of the wire. I'm going to assume this is the x-axis. You see how already we made it easier? So instead of having to deal with integrations in the x and y and the z direction, we're going to integrate only in the x direction, because that's where the wire is. And the summation, as I said before, is along the wire. So if I go back into the expression in here that we have seen, the summation is along the wire. So that's why I'm going to have this summation from negative L to positive L. Okay, so that makes it easy for me in a sense. So I'm going to go distance x and an element of length dx. Okay, then in this case, I can simply use the expression that I just found from Butin-Savart's law, where dl is actually going to be dx I hat, and I need to find where r hat is, and divide by the distance squared, then I'm in business. Then I have to sum from negative L over 2 to positive L over 2. So this is the distance r squared, or r itself is the square root of x squared plus y squared. So that's what needs to go in the denominator. This is I hat, this is j hat, okay? And the k hat, I'm not drawing it. Okay? K hat is coming out, coming from the screen, okay? This is the unit vector that I need to deal with, dr. I'm sorry, dr. I'm sorry, that's r hat. Okay, that I need to find its components. It's clearly, it has a negative component along the x direction, and it has a positive component in the y direction. And the negative component, this angle I'm going to call theta from the get-go. Okay, and this is the same angle theta. So from this coordinates in here, I'm going to assume, I will know that the x component is actually the opposite to theta, which is sine theta times the length of the unit vector, which is 1. So it's negative sine theta in the I hat direction. And the same thing in here, it's a positive, it's the adjacent to theta, so it's a cosine theta times the length of the unit vector, which is 1. So in the y direction, so the vector dr, the vector r hat. The vector r hat has this components, minus sine theta in the x direction, cosine theta in the y direction, and it has no component in the z direction. Clearly from this geometry, I call theta already this angle. Theta is such a way that is equal to, in this direction, where I'm looking at the opposite to the angle theta, the length of the unit vector is always 1. So the length of the unit vector times the sine of theta, which means it's a negative sine theta because it's in the opposite direction of I hat. And in this direction for the vector, in the y direction, it's a cosine theta because it's the adjacent times the length of the unit vector, which is 1. So it's a cosine theta. So this is r hat. We're done. Now I need to find dl. dl is clearly this element. Okay? And dl is equal to dx in length in I hat direction, period, end of the story. So dl as a vector has one component along the x direction, which is dx and 0 and 0. Okay? I need to form this cross product, and I know you guys told me that you did the matrix the representation. So the dl crossed with r hat then gives me the determinant I, j, k. The components of the vector, first vector are dx and 0 and 0. The components of the second vector are minus sine theta, cosine theta, and 0. Obviously, I need to find the x component first. And the x component I hat is equal to 0 times 0, that's 0, minus 0 times cosine theta, that's 0, minus j hat, the components of the vector j in this case, in the x direction, dx minus 0 times 0, that's 0, minus sine theta times 0, that's 0 also. So it has an x component that is 0 and a y component that is 0. And this vector, the cross product of these two, is only in the k direction. So it's plus k hat direction times dx times cosine theta, which is cosine theta dx, 0 minus sine theta, so it's 0. So minus 0. Okay. So everything vanishes except the components in the y direction. I mean, in the k direction, in the z direction, and it's expected because the whole picture with the current running on the screen, okay, and r itself and r hat are actually on the screen. So no matter what happened, the vector that is perpendicular to both vectors on the screen is a vector that is coming out of the screen or going into the screen. It cannot be on the screen. It has 0 components on the screen. As I said before, and this is the first question that Sebastian has raised, and this is actually the point of the discussion today, that you're going to always have the cross product of these two vectors perpendicular to the plane of where they exist. So this is the question today, and this is its answer. So the magnetic field is always perpendicular to the plane formed by the current, basically the wire itself, and also to where the direction we're calculating the magnetic field in it. So again, this is the question that Sebastian has raised, and I'm raising it back as point of discussion so that everybody remembers that, because directions are the worst part of this whole section. As a matter of fact, this entire 3 chapters, the direction is the biggest headache. So when Sebastian raised it today, he is 100%, 200% justified. So you guys need to pay attention to it. So that's the point of the discussion today. Does this make sense? For this particular case in here, where is the issue that I was? Yeah, this same thing in here. So in this problem in here, L is on the screen. R, where R hat is also on the screen. Okay. Be it they make an angle theta between them, that doesn't matter. Okay. Both of them, they describe the screen. The vector B in this case better be perpendicular to both of them which is not on the screen. As a matter of fact, has no component on the screen. Okay? Does this make sense for directions? Sebastian and everybody else? Yes or no, Sebastian? Because I have a remedy for that. Somewhat. Or an alternative, I should say. Come on, guys. Yes, no? Eric, Alex, Israel, Daniel. Okay. The alternative, if you don't know the directions or anything like that, is do exactly what I did. That is, try to do the cross product the old-fashioned way. Where things land, they land. Okay? Do the mathematical approach. You have to be very, very cautious with that only because you may have made a mistake somewhere in the vectors and you may end up with the wrong answer. So you really need the physics to help you recover from that situation. That's the only thing I'm going to tell you in here because there is no easy way, no easier way of dealing with this issue. Okay, no easy way of dealing with this issue. The physics is the following. B itself is basically the cross product of the DL where the current is running, the wire basically DL. So if DL happened to be this way, and the magnetic field is in this somehow in the plane that these two form, wherever they are, this plane actually, it's going to be perpendicular on them, the magnetic field. So it's going to be perpendicular on this plane. So if this is the plane, if this is, for example, where the wire is, and this is the direction of the that's I'm trying to find the magnetic field in this point, and the wire is running along this side. So this is the plane. The magnetic field in this point is going to be perpendicular to both of them. It's going to make a 90-degree angle with this direction, and it's going to make a 90-degree angle with the other one, so meaning it's going to be perpendicular to both of them. So that should save you at the end of the day. So if you want to, you could go the algebraic way, pure and simple from the get-go, okay? And use what you know about the cross product. At the end of the day, you need to look at your result. Does it even make sense? And it only makes sense if it is actually perpendicular to both of them. And this is exactly what happened in this situation. Because the answer at the end of the day was the cross product of where DL and R hat is perpendicular to both of them, has zero component along the X direction, zero component along the Y direction, and has only pure component along the Z direction. We're not done yet. All we did was just calculate this cross product. This one. I still have to multiply it by I divided by R squared and sum through the entire wire. Remember, the wire is of length 2L. So I need to still do that. So the magnetic field then, B, is equal to mu naught. I is uniform, so it's going to come out of the integral divided by 4 pi times the integral from negative L to positive L of this stuff, which is now we know. It is going to be cosine theta. Why did I forget the cos of the sign in here? Times dx over the distance squared. The distance squared is just this thing squared. Okay? The distance squared, which is x squared plus y squared, and times k hat. K hat actually is a constant too, okay? K hat is constant, so it can come out of the integral. And from now on, I'm going to drop the vectors altogether because I know it only is in the z direction. There is no component for this magnetic field along anywhere. So B is actually going to be in the z direction, okay, period. So there is no need for me to carry this k hat because I know it's constant, and there is no need for me to worry about the anything else in this thing in terms of directions. So that makes it easy in a sense. That's because we chose the right coordinate system. Now I have to do a transformational variable because I have this cosine theta, which really needs to be expressed in terms of x to solve this thing. And cosine theta is clearly from this geometry equals to y divided by this r. Instead, I'm going to make a change variable to where theta is. From this geometry, clearly you guys can see that tangent of theta is equal to, is equal to x over y. The opposite is x, and the adjacent is y. So I'm going to take advantage of that, okay? So I'm going to leave the cosine theta, but I need to find where this dx is in terms of this new change of variable. So I need to say dx, which is equal to y, d sub tangent theta, from the change of variable, which is equal to y, d sub theta divided by cosine squared of theta. That is one thing, okay? So I know, so I'm going to leave the cosine theta in the numerator times dx. dx is again y d theta over cosine squared of theta. So that is, y first, d theta over cosine squared of theta. What this term is just this one, divided by x squared plus y squared. So I'm going to take y squared as a common denominator, and I will be left with 1 plus x squared over y squared. That is actually tangent squared. Okay? Of course, the integration now is for theta. So theta now, the boundaries of integration need to change. So it's no longer that. So it's from this angle, which I'm going to call theta naught with a negative sign, to this angle, which I'm going to call positive theta naught. Having said that, then the integration will flip now, not from this, but rather from negative theta naught to positive theta naught. Now I have successfully done my change of variable. Now there is a y in here, and there is a y squared that I need to cancel. And y is constant. Y is the same everywhere. I'm trying to find it in here. So y is fixed. So I'm going to take the y as a common term from this integration. So the magnetic field in this point in here is going to be mu naught I over 4 pi times y. And the integration now of negative theta naught to positive theta naught. I'm going to tell you what theta naught is. It's simply, from this geometry, is clearly L, the tangent of theta naught is equal to L over y from this geometry. L over y, that gives you the tangent, okay? So that is arctangent of that thing in there, if you like, okay? So it's not hard to do. So I'm left with a cosine theta, secant squared, if you like that, d theta over cos squared, and 1 plus tangent squared, that's actually 1 over cosine squared theta. So actually this will bring you another cosine squared theta. This term will become this one in the numerator. The cos squared and the cos squared cancel. I did not write it secant squared. Had I written it secant squared, it's going to be secant squared times cosine squared. It's the same thing, 1. Okay? So no matter what you do, if you do this change of variable, that saves the day. The integration will become a lot easier. So at the end of the day, all I'm left with is the integral of cosine theta d theta, cos theta d theta, and that is sine of theta. So that is evaluated from negative theta naught to positive theta naught, the sign being an odd function, so it's going to be just twice one of them. As a matter of fact, this whole integral could have been changed now back into an integration from 0 to L, but multiplied by 2, because this whole thing is actually even in terms of x. The integrand is even in terms of x. You have an x squared plus y squared. The cosine theta itself is also an even function in terms of x. It's basically y over the square root of the same number, okay? So this function is even, so I could just have pulled the 2. So it's going to be a 2 mu naught I over 4 pi, and I know you're eager to get rid of that 2, which is fine, we will, okay, of sine of theta naught, okay? I already did the integration sine theta and evaluated it between theta and negative theta naught, and that's where the 2 came from. So this whole thing is carried over. And sine of theta naught from this geometry is clearly L over this hypotenuse. So I can write it in terms of L. So let's get rid of this 2 and the 4. So it's equal to mu naught I times L divided by pi times y square root of L squared plus y squared. Aren't you guys relieved? So this is the magnetic field produced by wire. Mu naught I divided by pi y times L over square root of L squared plus y squared. Any questions on how we did this integration? I know the book has it backward. I looked at the book already and have the wire actually running this way, and the integration actually, I'm sorry, it's running this way, but the integration over y, say they flip the signs. This is most of the textbooks how you do it. But again, if you like the book, you go ahead and follow the book. I'm sorry, did I miss a 2 in here? Yeah, there is a 2 missing. I just canceled one of the 4s. So it's still the same thing, okay? If you guys don't have any questions, I'm going to take the limit of an infinite wire, which is really of interest all the time. Infinite wire. Infinite wire, that means L squared plus y squared is equal to roughly L squared, because y squared is negligible. And the square root of L squared plus y squared is L itself. So this ratio of L over the square root of L squared plus y squared will be the same thing as the ratio of L over L, which is 1. So the answer in this case is, for an infinite wire, is this ratio becomes 1, and the magnetic field for an infinite wire should be equal to mu naught I over 2 pi times y. This is a very, very important result that I really need to circle it in here. So this is an infinite wire, and we found the magnetic field for it. Magnetic field of an infinite wire. This is an important result because this is a result that you can remember. And you do calculations within the lab and you try to compare things and things like that. So this is an important result. So again, we had already a point of discussion in terms of the directions, that the magnetic field already is perpendicular to all the plane that is formed between basically the wire, or at least the element of the wire, and the direction where we're trying to find the magnetic field. The second point in here is that the magnetic field produced by the wire is inversely proportional to the distance y. So that is the second point of discussion today that you guys need to raise. So B, inversely proportional to the distance from an infinite wire. Okay. Okay, this result is going to play a major role down the road when we come into the Ampere's law. So we're going to stop in here. We're basically, let me check exactly where we are in terms of the chapter. Okay, so we covered almost half the stuff. We still have the other half, which hopefully we'll finish it on Monday. And again, maybe we'll do a practice. And then also we'll have, I think with the homework is already assigned, so I'm going to do some problems from there toward the end. But then we have the lab on Monday. Okay. Any questions? So you have 2 points to raise today. Any questions today? Alex, how do you feel about this? And Sebastian and Eric and other guys. To the distance from the wire, for an infinite wire, from a distance of an infinite wire. Does this make sense to you, Sebastian? Okay. So if you happen to be under a power line, for example, that is carrying a current, so you can actually estimate how much the magnetic field is in there. Okay, if you have an idea how many volts that is carried by that wire. Okay, and you will see it's not that drastic how some people are basically trying to do things in there. Okay. Okay, so guys, I will see you. Let me stop first of all the recording.